with this, we're going to start talking about the limits of a function. And so we've been kind of tiptoeing around the notion of a limit when we looked at the long-term behavior, we looked at the behavior around asymptotes. And if you recall from the very first lecture that I gave, we had this thing where we drew a function, and then we chose 2 points on that function, drew a line between them, and then said the slope of that thing is going to be our the slope of the secant. The secant is the line that crosses the 2 points. And so I put that in the notation where you have x sub 1 plus delta x equals x sub 2, right? So we're really just looking at one value of x sub 1, and then we have this other thing that we're going to add to it to get to that second point. And so where this takes us is that if we make x a little bit smaller, of course we're going to get a value of our function that's closer to f at x plus 1, and that secant line is going to get the slope of that's going to change in value, and it's going to change in value, and it gets closer to the tangent as delta x goes to 0. So this is one of those things where now the delta x is going to be significant for us, because this is how the distance between x and x1 and x2 is that delta x is the difference. And so we're going to say we're going to bring that second point right down to the first point. We're going to watch that tangent as it or watch the secant as it comes down to and approximates that tangent.
You said again, this was chapter 2.2, right?
Yeah, we're starting into chapter 2.2.
From the pre-calculus?
No, from the calculus book now. Okay, so this is where that notation of the limit came in, and when we were looking at functions that had either long-term or short-term behavior, we were saying as x goes to, let's say, one of the vertical asymptotes from the positive or the negative side, we're really talking about this notion of limits right here. Okay, this notion, and that's what 2.2 in the calculus book is dealing with. Is we're going to define the limits, and we're going to figure out how to calculate them. Alex, you had a question?
Do we need to buy the calculus book now?
Well, you should have it. Yes, we've already done a section out of it.
We've done homework out of it?
Yes.
We did homework out of the pre-calculus.
Well, you should have it. Okay, so we're going to look at the definition of a limit. And so when we use this notation where we have this this limit, and you're going to have this x with a little arrow that goes to a, what that means is the limit of our function f at x as x approaches a equals L. So that means I'm going to take x and I'm going to get as close as possible to a, as close as you like, and I'm going to find the value that ultimately is the limit. So that's a little bit like me saying, where am I in the front of the room? I'm going to go towards that wall, and no matter how close I choose to get to that wall, that's as far as I'm going to go. I'm not going to go anything beyond that. So you would look at that wall as being the limit as I'm approaching it. Same thing here. We can get as close to that limit as we want by choosing an a, by choosing a distance, or choosing a value for x that gets us that close. Now it's important to realize here that we're not going to make x equal a. All right. So in many cases, we'll determine the limit by doing a substitution like this, but we're really going to think about this as it approaches it, not as it equals it. Okay, so we can be as close as we want. We can be like within a billionth unit of L, and we'll have some value of x that gets us there. And so that's really what the notion of the limit means. Okay, so the way we've done this before is that we've had the limits when we were approaching asymptotes, that we would say, okay, as x approaches this value from the left or from the right, if we put a with a little negative in the superscript, that means we're coming from the left. We're coming from the negative side. Okay, that doesn't mean that we're going to the negative side. That means we're coming from the negative side. So we're coming from the left. And we call this a left-hand limit. And similarly, if we put the little plus right above as a superscript of the a, that means we're calculating the limit of f at x as x approaches from the right. Okay, so just think of these things as when it's plus, that means you're going to start from the right and come towards a. The other one, you're going to go towards a. So if you look at it graphically, if we just put a on a number line, of course we're going to have a vertical axis as well. But here we're looking at choosing x so it gets closer and closer to a on as x goes to a from the positive side, it's going to come from the right. It's going to go to the left. Now here's a definition that we're going to stick with, and this is going to be a pretty important notion, that we're going to say that the limit as x approaches a, the limit of our function f at x as x approaches a is going to be L if and only if the left and the right hand limits bring us to the same value. Okay, so let me just draw on the board a function. And let's say we have a function that is discontinuous like this, and this is our value a. This does not have a limit, because when we approach a from this side, we're going to get this value, and when we approach it from the left-hand side, we're going to get a different value. All right, so what we're going to say is that the limit only exists, and it's only defined for when we get to the same value, whether we go from the right or the left. Okay, so let's look first at a numerical example. So what I want to do is take this polynomial function, and I want to estimate it as x goes to 1. And so what I'm going to do is I'm going to take values and I'm going to get them progressively closer to 1. You see I start out with 0.5 and I'm coming from the left going to 0.999, which is going right, coming from the left, and then it's just the opposite on the other column where I'm going to take something above 1 and then get progressively closer to the point where I have a very small difference between x and a. Yes?
So how is this different from just like a very small secant line? Like what's the difference?
It is. Well, a secant line, we're talking about having rates of change, and we're approaching a limit for a rate of change. Here I'm just talking about the limit of a function. There's no secant line involved. This is just the function itself.
Oh, okay.
Okay? Yes, Carol.
Going back to what you said about on the board, because there's another function that is like intersecting at a, or like is at the same point as a, the limit doesn't exist?
Yeah, we say the limit doesn't exist because
it can still keep going.
the right-hand limit is different than the left-hand limit.
Okay.
Okay, and that's the only difference. So yeah, ultimately we're going to get to the limit of that difference quotient, which will give us the derivative. But first we're going to learn how to do limits in general. Okay, so we're just going to look at the functions. All right, so I did a little number crunching, and so these are the values that I get. And so what do you think my limit is? I mean, it's pretty plain. They're both getting very, very close to 2. And if I use numbers of x that are even closer to 1, we're going to get even closer to 2. And you would expect this, right? Because if you plug in a 2, you get, or if you plug in a 1, you get a 2. So what we say here is that the limit as x goes to 1 of this function equals 2. All right, so you can either put the function notation f at x, or you can put the whole function in there. And oftentimes this is just a little shorter. You're taking the limit of this expression. Now you say, so what's the big deal? Why don't we just plug in the number? All right. Well, let's look at a different example then. And this will be posted. Don't feel like you have to write all these numbers down. So let's have a function now where we're going to have x squared plus 2x plus 1 over x squared minus 1. Now, we'll just take this at face value like this, but one of the things that I want to point out is that if we factor it, we're going to get x plus 1 squared over x plus 1 times x minus 1. And so when we cancel out the x plus 1's, we have a domain restriction that x cannot equal negative 1. Okay? So now, what I want to figure, though, is as x goes to negative 1, what is my limit? What would it be? Now, if I just plugged in negative 1, I'd get 0 over 0, and that tells me nothing. 0 over 0 doesn't represent anything. It doesn't mean infinity, it doesn't mean negative infinity, it doesn't mean 0, it means nothing. It's indeterminate. So if I notice that my middle value here among all these values is x equals negative 1, I can make a plot and see what this looks like. And so, we've done this before where the horizontal asymptote is a 1 because x plus 1 over x minus 1 is the same degree and the coefficients are 1 over 1. We have a vertical asymptote at x equals 1 because that x minus 1 in the denominator gives us that vertical asymptote. But we also have this domain restriction where x cannot equal negative 1. And so I just circled that's a place that we can't evaluate the function. And if I were to make my graph, if I were to ignore that, that domain restriction, I would just have this, this kind of transformed toolkit function of 1 over x. Now we have x plus 1 over x minus 1, so it's shifted to the upper left. I have to exclude the negative 1, so I put a hole there. That was, you had that on the exam where we had the instance where we make a hole. But if we look at what these values turn out to be, if we calculate this, we'll see that as I go from negative 0.9 down to negative 0.999, I get closer and closer to 0. And if I go from negative 0.1 up to negative 1.001, I have the same trend. I'm getting closer and closer to 0. So this is what you would expect, right? Where you just basically have this hole because the x plus 1 over the x plus 1, when x is minus 1, that's going to be 0 over 0. So that says we don't have that as part of the function, something that we can calculate in the function. But we know that if it wasn't there, it would simplify just to that x plus 1 over x minus 1, and we would have the smooth graph. So we have this hole. So what's important here now is that I can say the limit of f at x as x goes to negative 1 is very clearly 0, even though negative 1 is not part of the domain of the function. My left and right hand limits are the same, and I'm pointing to that thing, so I actually get a limit. So I'm getting a number, I'm getting the limit, that's a number that really represents where that hole is. Yes?
Sorry, is the only, you showed possibly two holes, but the only hole is the x equals negative 1, not the negative 1 on the, that's not a hole, right?
And that's a very different question. That would be the limit of f at x as x goes to 1. Okay? So as x goes to 1, if we look at it from the left, it's going to go to negative infinity. If we go from the right, it's going to go to positive infinity. Since they're different, no limit exists here. But clearly, at the x going to negative 1, both go to 0, where that hole is. And so the left and right-hand limits are the same. So we're going to say that the limit is, the limit of f at x as x goes to negative 1 is 0.
So we only have limits, like it's the same thing. We only have limits when we have a hole, when we have something in the numerator and in the denominator that cancels each other's out. That's the only time we have a limit?
Well, no, we're going to have limits all over the place. This is an example of one that we have a function that has a hole in it, and that we can still talk about the limit existing at where that hole is. Like in the previous example, we had we just had a continuous function, and so the limit equaled the function's value. Yes, Alex?
Why are the x values there what they are, like tiny little decimals?
Those are arbitrarily chosen, okay? So I basically just said, what happens if we get really close? So I'm starting far away and I get closer and closer to see the trend.
Okay,
Okay, one value won't tell me a trend, but this, to me, looks like a trend.
so you're getting close to x on both sides.
Exactly, Kiara.
I still don't understand how you got the limit equals 0. I'm so confused.
Okay, all right.
Yeah.